Start with any questions? Anyone about to come up with a question? All right.
I'm still not 100% on the graphs. I mean, I've looked at them and tried to understand them, but I'm still not completely there with them.
You mean the phasor diagrams?
Yeah.
Okay. Well, let's run through the same problem. I know I touched on it at the end of class last time, but let's actually run through the full problem, except without using phasors at all. Okay. And maybe that just works better for you. So it was AC power supply, resistor, inductor, and then capacitor in parallel with that. And this was 15 ohms, 45 millihenries, 200 microfarads. And we established that the RMS value was, or given 120 volts, and then that led into the maximum for the power supply, max, with a labeling as epsilon sub 0 was 169.706 volts. This is just the preliminary stuff. If you have questions on it, just please ask, but I was just zipping through the preliminary stuff. Is everyone good so far? Established also that the frequency was 60 hertz. And so the angular frequency ended up being 376.991 radians per second, and that's because this is equal to 2 pi times the frequency. Once we had omega, we could find x of L and x of C. X of C is 1 over omega C. And so that was 13.263 ohms. And x of L, which is omega L, 16.965. I have an extra 5 here. I'm starting to figure out. I think that was.
I've got 16.965.
Okay, there's not 2 5s there?
Not too bad.
Okay, all right. All right, so when dealing with this from a complex number point of view, as mentioned last time, I'm going to use J to be the main imaginary number. And so there's a resistance equivalent for each of the components. So for the resistor, it's just 15 ohms. And it's all ohms. For the inductor, it is J times X of L, so 16.965 ohms. And this would be negative J X of C, so 13.263. Or writing that out slightly more formally. And what I did last time was sort of the double impedance for a component. So for an inductor, it's J times X of L. For a capacitor, negative J X sub C. And for a resistor, it's just R. I don't think I wrote that last time because I was just using R. All right, so we're basically going to do a Kirchhoff bit here. If I'm going from the bottom junction to the top junction, I have 3 different paths to go. I should get the exact same potential difference either way I go. So whatever I get across the power supply, first let's just do the capacitor. What I'll get across the capacitor. So therefore, the voltage across the capacitor should be the same voltages across the power supply because they're the only 2 components along each path. And that's just gonna be the magnitude, 169.706 volts at an angle of 0. And I don't know, it was established last time, I expressed it at some point. I'll just say that the phase or the voltage for the power supply is 0. You just have to establish a reference somewhere, and I'm just making the power supply to be my reference. I know that voltage is equal to current times voltage across the capacitor is equal to the current across the capacitor times the impedance of the capacitor. It's supposed to be a Z there. Well, I know what VC is and I know what ZC is, so we can easily solve for the current across the capacitor. That's just the voltage across the capacitor over the impedance across the capacitor. So that is 169.706 at an angle of 0 divided by, it is there it is. Now in terms of the angle, that's sort of rectangular form over here. To get it in polar form, we just sort of imagine our complex number plane, where I've got a real axis and an imaginary axis. Negative J 13.623, well, negative J is that way. There is no real part to it, it's all imaginary. So it's down 13.263. So this is 13.263 at an angle of negative pi over 2. And so I can now find the current across the capacitor by taking that bit right there, and then subtracting the angles. 0 minus negative pi over 2 is pi over 2, and whatever that number is, 13 point something. And we're about to have it revealed. Or 12 point something.
1.27. 1.27.
This divided by that? It's 169.706.
Let's do this one. Yeah, 12.79.
Units?
Amps.
Because it's current. This is a volt per ohm. All right, questions to hear?
Why was it negative J 13.2? Like, how do we know that one's negative and the other ones are positive?
It ultimately comes back to that the voltage lags for the capacitor and leads for the inductor.
Okay.
I mean that.
Yeah, I remember
Why, when 0 is divided by negative pi over 2, why isn't it 0?
They're subtracted, not divided.
Subtract.
Because this represents 169.706 e to the I omega t plus 0. And down here you got the 13.263 e to the I omega t minus pi over 2. And so when you do that division right there, you end up with
Subtraction.
0 minus the negative pi over 2.
Gotcha. Just curious, I'm sorry.
Yeah, this, I mentioned that last time, but probably very quickly at the end. But this, just the shorthand notation, I know that when I have it in polar form like this, when I'm doing the division for the AC circuit problems, when I'm dividing, I'm subtracting the angles. Okay, other questions up to here?
What are the labels on that graph?
This,
Yeah, at the top.
real and imaginary, RE and IM.
Okay.
It's basically taking our phasor diagram where I have the two axes like this and just calling it, hey, we'll call this the real part and this the imaginary part. And the instantaneous value is whatever the real part is at that moment. Other questions? All right. And again, what we're trying to find out here, we need to figure out basically eight equations here. We have the voltage of the power supply, we have voltage of each component, and then we have the current of power supply, and then each of the other components. And so at this point, the voltage of the power supply and the capacitor we got, they're the same. Current of the capacitor we just got. I know the current for the resistor and the inductor are the same because they're in series. So let's do that one. The impedance for the RL branch, that path right down the middle. Well, I just add them. That's 15 plus J 16.865. No, 965. Let's get in polar form. So imagine that we're dealing with a real and imaginary axes here. So I go 15 in the real and then 16.965 in the imaginary. I have some angle here, phi. This is 15. This is 16.965. So it's just like converting, just think of a vector, converting I have an ij components and put it into polar, so I need a magnitude and an angle.
Magnitude 22.64.
Okay? And it's a first quadrant angle. Get the angle in radians would be appreciated.
I got 0.8468.
8468.
Yeah.
So what was that? Remind me how to get the.
No, the tangent of phi is 16.965 over 15.
That's right.
And I suspect all of our calculators, there's some button that you just hit and it'll automatically do it for us.
Yeah, I got 0.8. Yeah, 0.847. Or 0.848.
What, 84? You had 848? And you had, I'm curious, I mean, it's not a huge difference there, and I wouldn't notice it on grading a test or a quiz, but I'm just curious about what the difference was.
0.84679, but it's
Oh, okay.
0.8468. Yeah, sorry about that.
Okay.
We got that on the
Okay.
last one.
So, that is the impedance down the middle here. So if I want to find the current, I just do voltage divided by the resistance, by this impedance. So the voltage down the middle, like that equation first, voltage down the middle will be the current down the middle times the impedance down the middle. Again, it's just an Ohm's law variation here. The voltage, I know it's 169.706 volts. It's not, I'm not doing the voltage across each one individually, I'm doing for the whole thing at an angle of 0, divided by 22.64 at an angle of 0.84679. And so we got our math piece here, which will tell us the magnitude of this current. Start writing this stuff down somewhere. So I see. So this is my current down the middle. And what do we get?
7.495 amps,
495 amperes at an angle of,
negative 0.84679.
yep. So at this point, we now have those two currents under our belts. The voltage across the resistor is just the current across the resistor times the impedance across the resistor, which is just the resistance. So that's 7.495 amperes at an angle of negative 0.84679 times 15 at an angle of 0. Just play it. The resistance is just all real. So we multiply these two together in order to get the magnitude of the voltage, and then just add your angles. So 15 times the 7.495.
112.425.
Units?
Volts. Yes.
At an angle of,
0? Multiplying?
just like when we divided the angles, we subtracted, we're multiplying angles.
Oh, you added, oh, so negative point.
Yep, 84, I think that's a 679,
Okay.
whatever number that's supposed to be.
Oh, exponential, I gotta remember that, okay.
And then the voltage across the inductor, now we could do it two different ways. I know what the total voltage is, I know what it is for the resistance, so I could subtract. But subtracting polar form is not particularly the simplest thing, so let's do it the easier way. VL is equal to IL times ZL. So that's the current, well, it's the same as we just used, that's 7.495 amperes at an angle of negative 0.84679 times my impedance across the inductor, which is 16.965 ohms at an angle of pi/2, because it's a positive imaginary number. So we got our calculator piece right there, and the other one, probably a calculator also, since we're dealing with pi/2.
127.15 volts.
Angle I had 0.72400.
0.72400.
Yeah.
So we now have VL and VR. And now we're at the hardest part, the last bit. The current from the power supply, I know it's got to be the sum of the other two currents. Since they're in polar form, adding is not necessarily the easiest thing. It's easier to, we'll have to get it in a rectangular form. It's not complicated, but it's the most complicated piece we're doing here, math-wise. So the current from the power supply is the current going down that middle path plus the current going down the right side. So we're adding 7.495 amperes at an angle of negative 0.84679 plus capacitor, which is 12.79 amperes at an angle of pi over 2. And to put it in rectangular form, it's just that times the cosine of that angle, plus that times the sine of the angle, plus, same thing over here. Now this one I can do in my head. So this would be J 12.79 pi over 2, straight up. That one is a fourth quadrant angle, whatever that happens to be. Or for those who missed what I just said, what we're talking about here is, again, I got my real and imaginary axes here. At that angle, so basically I have this 7.495 magnitude. Think of it as a vector and an angle here of 0.84679 radians. And we're breaking it up into components. Anybody done this already?